In this video, we're going to talk about reconstruction of the signal at few different methods. But before we get there, I just want to kind of come back and use this as a way of kind of positioning ourselves, what we are up to with these sampling theorems. If you recall, we've always talked about the fact that the real world, as we know it, it's continuous time. In other words, when we sense the world, when we control the world, we get x of t. It's continuous time, analog, in other words. And then we typically would like to operate on that in a digital world, which means we can't have curves. Rather, we got to have a series of numbers representing the signal. So in order to do that, we basically were able to sample it using our p of t. Okay, and then what we get back out here is x of n, or we call it xp of t, or we call it xp of nt, where this t is the sampling period. And then once that is done, that's great. That's what we've been doing so far. We've talked about the fact that if you want to sample this, that you want to be able to reconstruct this thing, you need to be able to use the right frequency, right number of frequency, right frequency to be able to recover them. So what do we mean by that? We basically mean that the sampling rate, omega, which is 2 pi over sampling period, has to be larger, not equal, larger than 2 times the maximum frequency of the signal. In other words, if I plot the signal, and there should be no content, everything above omega 0 and everything below minus omega 0 has to be 0. So this was, we called it the Shannon-Nyquist sampling theorem, or just simply sampling theorem. This is great. The reason we did this is so we can use this in a computer or someplace and manipulate the numbers to do whatever it is we are trying to do, or store the data, or whatever the case is. Now, the next step is I want to recover. My real life curve looked like this. In here, I got a bunch of numbers over, first sample, second sample, third sample, fourth sample. I want to be able to basically use these samples I've got to recover the original signal. Now, so we follow this rule, which is the sampling theorem. So we know we have enough content to be able to recover it. Now the question is, how do we recover it? And that is the whole signal reconstruction, using kind of interpolation is a fancy way of guessing which shape does it have between the sample. If you remember, I don't have any data between the samples. I know what the value of the original x of t was here. I know what the value is here, but I have no value in here, so I have to make some assumption. And that's called interpolation. So let's go take a look at the simplest form of interpolation. This is called zero hold. And this is the simplest one. Oh, actually, I'm sorry. Let's back up. Let's back up with the this actually is not a zero hold. This one is the zero hold. So let's take a look at the zero hold. The zero hold is one of the simplest way we can recover, and all we are doing is we're basically saying, look, what we're going to do is this was the signal. This is the signal we sampled. Right here is what we sampled. And what we're going to do in this diagram here is basically saying, when I hit the sample here, I'm going to, because I don't know what's between the two sample points, I'm going to hold it the same and then come back up. And so this is this way of doing it is called zero hold. So as the sample comes in, I hold that sample till the new sample tells me a new value. That's the simplest way. Now, if I want to step up from there, the next one is called, the red one is going to be called the one hold. And instead of doing that, what I will do, I would multiply by a linear line, which basically goes like this. So I would extrapolate between this point and assume in the middle is a linear line. So as you can see, I'm getting a little closer to, oops, that's not going to go there, that's going to go there. So that's called one hold approach. Now the ideal approach, of course, is what we talked about earlier. The ideal approach is this one. And in the case of, so this would be ideal approach. ideal method, if you want, of interpolation. What we basically are saying is that we're saying, look, this was the way you sampled it. You want to recover it, just put it through a low-pass filter. So this is going to be a low-pass filter. And if this low-pass filter, remember, these things are alias, right? When we took the signal that has a maximum frequency of omega m or minus omega m, we put it through our sample and we got something with aliases, and these guys are the aliases, right? And then this this other piece, we actually would like, when we want to recover it, we just want to get this. So if I could get a cutoff frequency, that cutoff frequency was between these 2 points, and I can do that because we said that this omega c is going to fall between these 2 points, and since I made an assumption that omega s is bigger than twice the omega m, I'm going to have plenty of space, not plenty, but it's going to have space to put my omega c's in here. So if I take an omega c, then I can recover and get my full signal back from that. If you put it in the pictures, what's going to happen is that, and the green is going to be this color, that what I'm going to get back is literally going to be more or less what the shape I put in there. Okay, let's put them all together so you can kind of get a sense of it. Let's say this is putting it in terms of transfer function. If I'm doing a zero hold, that was, remember, I just hold the sample for the period, and my filter is really kind of loosey. The characteristic of it is very flat as it goes around this dashed line that I'm overlighting. Now if I step up and let's say do the first hold, then I get a little closer to the ideal low-pass filter. Of course, if you do low-pass filter to recover the whole thing, that would be the best. But the thing is, you never can do this. In ideal filters, there's no such a thing as an ideal filter. So we either do zero hold or we do first hold, the most common. The other one is, the other approach is maybe higher order hold. It would be, you know, when I've got my samples going through, if I knew what the signal really was about, then maybe I can predict, maybe this is a parabola, or maybe this is some sort of equation. Because I understand the nature of my data, I can apply that and get a better result. But generally speaking, for what we are talking about here, first zero order, first order, and it's really the two approaches we use. And ideal is, well, ideal. We will never be able to do that, but it's good theoretically to know what's the best you could do. Okay, that brings us to the end of this interpolation, and what we basically talked about is the fact that, you know, ideally we have the sample because we want the numbers to represent any real phenomena we are observing, because numbers are a lot easier to store in a computer and be able to massage it, work with it, but then eventually we have to get that signal back out, and that the process of interpolation and recovery has to do with how you get that sample, that x of p of t, to an estimated recovered signal. And we talked about that the ideal filter would be the ideal method would be the best, but that's not real. In reality, you can't do that. The simplest and the cheapest way to do that economically is zero hold, because you just simply hold the filter. The next level of complexity would be to take this point and draw a line and say that's my curve, and so that's it. And this curve is just showing the transfer function for each of those methods we just talked about. That brings us to the end of this video.